Welcome back everyone to the openStars video series. This is episode 1 in the series, which is actually the second video. The first video in the series was what I called episode 0. And episode 0 was a short video where I talked about what this series is going to be about, who it's for, what people can expect to get out of it, what level it's aimed at, and how we're going to be doing things. And in particular, in episode 0, I talked about the special role that will be played throughout this series by the Greystar 3 Virtual Star Simulator, which you can see running here. So if you haven't had a chance to see episode 0, I recommend that you go back and take a look so that you'll know the context and know what it is that we'll be getting into here. So at the end of episode 0, I promised you that in the first episode, our discussion would be motivated by a question about the color of stars, which is sort of a fun topic to think about. And it turns out that understanding the color of stars leads us to some very important insights. If you go outside and look at the night sky with your naked eye, then it will look something like it does in this image here. This is actually an image that I found on the Wikipedia page on constellations. So let me just click on that and blow it up. So if you go outside and look at the sky with the naked eye, the stars look something like this. They all sort of look like they're the same color, sort of pale blue-white. But it turns out that's a misleading impression. The human eye just doesn't respond very well to color when looking at faint objects. To get a better sense of what the situation really is, it's better to look at an image like this one. This is an image that I found in the online Hubble Heritage Gallery. This is a gallery of images taken with the Hubble Space Telescope, maintained by the Space Telescope Science Institute. This particular image is of a feature known as the Sagittarius star cloud, but for our purposes it could really be any star field. And what's useful about this image for us is it shows us that stars actually come in quite a variety of vibrant colors. So there are some stars, let me zoom in here a little bit. There are some stars that are distinctly yellow, like these ones here, much like our own sun. There are other stars that are distinctly red, orange in color, like this one. And some famous bright stars in our own sky that have this red color are Betelgeuse in the constellation Orion and Antares in the constellation Scorpio. Then there are other stars, like this one, that are more blue-white in color. They really are that color. And some famous bright stars from our own sky that have that color are Vega in the constellation Lyra and Sirius in the constellation Canis Majoris. So it's nice that stars come in these various colors. It makes them nice to look at. But it's also important for another reason. It turns out that these different colors give us an important clue as to the nature of stars. The fact that stars have different colors tells us that stars are not all the same, that there must be something about stars that differs from star to star that causes them to have different colors. And so our question is, what is that something? What is it about a blue star that makes it blue that's different from a yellow star that makes it yellow, or that's different from a red star that makes it red? That's the question we're going to address. But first, let's talk a little bit more about color. We're used to thinking of color as being a quality or an impression that we have of an object in daily life. But color can also be measured and expressed precisely as a numerical quantity. So the first thing to understand is that any kind of light, including the light emitted by a star, is a form of energy. Light is radiant energy, or radiation. Radiation is just a general term that refers to energy that travels through space along rays, and that includes light. So we can measure the brightness of an object by measuring how much light energy we intercept from it with a detector. And in fact, this is something you actually do all the time in your daily life. Every time you take a picture with a camera, including the digital camera in your cell phone, before the camera actually takes a picture, it measures the amount of light hitting its detector so it can calibrate the exposure. In astronomy, we use the word flux to talk about the amount of brightness energy or light energy that we intercept with a detector from a star. Okay, so the next idea is that for any given star, let's say we pick on this star right here, this bright blue one, we can measure its brightness energy or its flux multiple times through different color filters. So for example, we could measure this star's flux as seen through a blue filter, a filter that only admits the blue component of that star's light. So that would give us a blue flux or a blue brightness energy. We could then measure the flux from the same star a second time, this time through a yellow filter, a filter that only admits the yellow component of that star's light. Then we could measure the same star a third time, this time through a red filter, and get a red flux. So at the end, we would have three different flux measurements for one star: a blue flux, a yellow flux, and a red flux, and they would all be different. And by comparing these three different color fluxes, we can come up with a set of numbers that will express that star's color precisely numerically. So that procedure of measuring a star's brightness energy or flux and measuring it through different color filters in order to numerically measure a star's color is known as photometry. So that has the same root as the word photography, photometry, photography. They both have to do with measuring or recording light. So as always in this openStars video series, we're going to use the Greystar 3 virtual star simulator to investigate. So since this is the first episode where we're really getting into this, we'll spend a little bit of time just doing some basic orientation here. So when Greystar 3 first loads in the web browser, it comes up in the mode that you see here. This is the default mode. So at the top here we have a number of input control panels, and throughout most of the videos in this series we're only ever going to need to think about the first control panel, the one that has a green background color that you see here. In fact, what I'm going to do is I'm going to hide the second panel since we won't really need it. So in that first panel we have four control knobs that control the simulation, that tell Greystar 3 what kind of star we want to simulate. And in today's video we're only going to need to think about the first knob, the knob that's on the left here. And I'll come back and I'll say more about it in a few minutes. Now down below here, if you scroll down, we have the output section, the output panels, and they contain a number of things that show us various aspects of the star that we've simulated. Throughout most of these videos, we're only going to need to think about the output image that's on the left here, the one that's labeled stellar disk. This is an image that shows us what the star that we've simulated looks like if we were close enough to that star that we could see it as an extended object with surface details that can be made out, as opposed to just looking like a point source like stars normally look. Now when Greystar first loads, by default it is simulating the sun. So if we go up here to the top, by default these input controls will be set to the input values for the sun. And if we come down here in the output section, this image that you're seeing is an image of a simulation of our own sun. Now, of course, in the spirit of science, you should be skeptical and critical in the best sense of those words. You might wonder, how realistic is the Greystar 3 simulation? How good a job is it doing of simulating something that's actually like the real sun? How does it compare to the real thing? Now, of course, what you certainly should not do is you should not go outside and actually look at the real sun in the sky. Not even once, not even for a second, not even with sunglasses on. The real sun is so bright that it can quickly cause permanent damage to your vision, and it can happen very quickly before you even realize what's going on. And sunglasses certainly were not designed to protect people from looking directly at the sun, no matter how expensive they are. So we don't want to do that. If you do want to compare the Gray Star 3 simulation to the real sun, the way to do it is to look at a nice image of the sun like this one. And once again, I'm going to Wikipedia again. If you do want to find a nice image of the sun that shows us what it would look like as our naked eye would see it, then what you're looking for is a white light image of the sun like this one. So this image was actually made during the transit of Venus. You can see Venus up here in front of the sun, but we're not going to talk about that. We just want to compare the real sun to the Gray Star 3 simulation. And the first thing we can compare, of course, is the overall color. And you can see that the Gray Star simulation sort of gets it right, that the real sun is kind of yellow, maybe yellow with a bit of orange, and so is the Gray Star 3 simulation. So that's good. Going into a little bit more detail, you can see that the real sun is actually not a uniform disk, that there's actually a radial brightness gradient where the sun is brightest at the center and then gets darker as you go towards the edge, or what we call the limb of the sun. And there's also a color gradient. The color is most yellow at the center, and then it kind of fades to orange and almost a red as you go towards the limb. And if we go back and look at the Gray Star simulation, we can see the same behavior, that we get the same kind of radial brightness and color gradients. So Gray Star 3 seems to be getting some of these details right, so we can be confident that the simulation is reasonably realistic. Okay, let's go back up here to the top, to the first input control panel, the one that has the green background color. For today's investigation, the input control knob that we need to think about is this first one on the left here, the one that's labeled effective temperature. So what exactly is the effective temperature of a star? You can think of that as being synonymous with surface temperature. So effective temperature is the proper astronomical term, but whenever you hear that, if you just swap in surface temperature, then you've got the right idea. Now, there's something about that might be bothering you a little bit though, because what do we mean by a surface temperature when we talk about a star? As you may know, stars are composed of gas. They are gaseous all the way through from the top right down to the center. And so stars don't actually have a solid or a liquid surface the way, say, Earth does. So how can we talk about a surface temperature for an object that doesn't really have a surface? Well, stars may be composed of gas all the way through, but they are not transparent. The gas that makes up a star is so dense and thick that it is opaque. From an outside observer's point of view, you can only look into a star a little ways and then you can't really see any deeper because the gas becomes opaque. In fact, while I'm talking about this, why don't I scroll back down here to the image of our simulated star. Looking at a star is like looking into a really thick bank of fog that you can't see all the way through. You can see in a little ways, but then you can't see any further, and as a result, the fog bank appears to have a white surface beyond which you cannot see. Same thing when you're looking at a star. So that deepest layer that we can see sort of presents the outside observer with an apparent surface, or you can think of it as being an effective surface. And the effective temperature is approximately the temperature of the gas at that effective surface. The next thing for us to think about is the unit for expressing temperature. And in astronomy, the preferred unit is the Kelvin, abbreviated K. So we're on the Kelvin temperature scale here, and that's different from the Fahrenheit temperature scale, and it's also different from but related to the Celsius or the centigrade temperature scale from the metric system. So once again, I'm going to a Wikipedia page here. We scroll down. There's a picture of Lord Kelvin, the 19th century British scientist after whom this temperature scale is named. And if I keep going down, there's a nice image here that shows us what's going on. So we have the Celsius or the centigrade temperature scale here on the left, and we have the Kelvin scale on the right. And the only difference between these two temperature scales is in the definition of the 0 point. By definition, a temperature of 0 kelvins is equal to minus 273 degrees Celsius. So on the Kelvin scale, the 0 point is 273 degrees lower than it is on the Celsius scale. So as you can see in this picture here, 0 degrees Celsius corresponds to plus 273 Kelvin. A nice thing about these two temperature scales is that the size of 1 degree is the same. You can see all the tick marks line up with each other here all the way up and down the scale. That if the temperature goes up by 1 degree Celsius, then it also goes up by exactly 1 Kelvin. So the difference is really just an offset. So to convert between the two, if you have a temperature in Kelvin and you want to convert it to degrees Celsius, you would just subtract 273. Or if you have a temperature in degrees Celsius and you want to convert it to Kelvin, you just add 273. Now the truth is that for stars that are relatively hot, that have effective temperatures of 10 or 20,000 Kelvin or so, this difference hardly matters. A difference of 273 is just a drop in the bucket. So for relatively hot stars, it almost doesn't matter which scale we use, degrees Celsius or Kelvin. But strictly speaking, we should use the Kelvin temperature scale. The Kelvin temperature scale is also known as the absolute temperature scale. So Kelvin temperature, absolute temperature, those are synonymous terms. And the reason for that term is that the way the Kelvin scale is defined, if an object has a temperature of 0 kelvins, then it contains no heat energy at all. So of course temperature is just a way of talking about how much heat or heat energy an object contains. On the absolute temperature scale, a temperature of 0 Kelvin means no heat at all. So in that sense, the Kelvin scale really makes a lot of sense. So let's go back to gray star 3 here, to our input control panel, and look at our first knob here, the knob that controls the effective temperature of the star that we're going to simulate. And let's think about the range of effective temperatures that gray star 3 will allow. So we can grab a hold of this knob here, and first let's try turning it counterclockwise so that we're turning the temperature down. Gray star 3 will let us turn the temperature down all the way to about 3500 Kelvin. And that's as low as it will go. 3500 Kelvin is about the effective temperature of the coolest stars that we would traditionally recognize as normal stars. There are objects out there whose effective temperatures are lower than 3500 Kelvin. Those are objects known as brown dwarfs. But those objects, because they are so cool, they don't really glow very brightly with visible light, so they don't really show up in the sky as traditionally recognizable stars. More importantly, brown dwarfs have some complications that make them very difficult to simulate, so we can't really simulate them with gray star 3. So our lower limit is going to be 3500 Kelvin. Okay, let's grab a hold of this and now turn it the other way, clockwise, up as high as it will go. And the highest effective temperature that gray star 3 is going to accept is going to be 25,000 Kelvin. So 25,000 Kelvin is a pretty high temperature as far as most stars go. Now it's not the highest temperature. People have found stars with effective temperatures as high as 40,000 Kelvin or so. That's about as high as it goes. But there's really two things here. The first thing to realize is that stars become a lot rarer as the effective temperature increases. Hot stars are rarer than cool stars, and there aren't really very many stars out there whose effective temperature is larger than 25,000 Kelvin. More importantly, once a star's effective temperature is much over 25,000 Kelvin or so, that star becomes less stable than cooler stars, and it starts to behave in exotic ways that are very difficult to simulate. So we can't really simulate hotter stars with gray star 3. So 25,000 Kelvin is as high as we go. But that's pretty good. That range, 35,000 to 25,000 Kelvin, pretty much covers all the stars out there that you are likely to find. So now we are ready to do some experiments with gray star 3 to understand why different stars have different colors. Now, one thing that's going to be part of our practice here is that we want to always do experiments in a very controlled way. So for that purpose, we always want to use the sun as our reference object. The sun is a very well understood star. We know its properties very well. If we simulate some other star and we're trying to understand its properties and put them in context, the best way to do that is to compare them to the properties of the sun. So our practice is always going to be that before we do a series of experiments, we're going to want to put gray star 3 back to the values for the sun so that we're simulating the sun first. Now, of course, the problem is that I have messed around with this effective temperature dial, and it's no longer indicating the correct effective temperature for the sun. So first I would need to fix that. I want to put this back to the sun's value, but that's a little bit of a problem though, because maybe I don't quite remember what the effective temperature of the sun is, and so I don't quite know where to set this. However, not to worry, because there is a very easy way to get gray star 3 back to the sun's values if you get lost, and that is simply to hit the reload button. Right, so on every web browser, you can always hit something that will reload the page, and when gray star 3 reloads, by default it automatically goes back to the sun's input values for all the properties. And so there we are back to the sun's effective temperature again, 5,800 Kelvin. So that's kind of a neat little trick to keep in mind, especially if you're a teacher or an instructor using this in the classroom. If you lose your way, there's an escape hatch. Just hit reload and you are back to the sun, our primary reference object. Just going to hide this panel again. Okay, so now we're ready to begin doing some experiments. So we're starting at the sun's effective temperature, and I'm going to start off by going down in temperature. So let me grab a hold of this and let me turn it down. It's a little bit hard to be exact with this, but that's okay for these purposes. I want to turn this down to about 4,500 Kelvin or so. So I've just decreased the temperature by about 1,300 Kelvin from that of the sun. So let's see what happens if we simulate a star that's 1,300 Kelvin lower in effective temperature than the sun. So what I'm going to do is I'm going to come down here. Let me just zoom out here. So the image of the star that we're simulating is still the same. It's still the sun because I have not yet hit the model button. So what I'm going to do is I want you to keep your eyes on the image of the star that we're simulating down here, and I'm going to go up here and I'm going to hit the model button, and we'll see what happens. Okay, so gray star 3 took a second or two, and what it did is it recomputed the simulation. It's now simulating a star whose effective temperature is 4,300 Kelvin. And if you watched what was happening, you might have noticed that the color in the image of our model here just changed. It now looks less yellow and more orange. So by turning the effective temperature down, our star its color has changed more towards the red end of the spectrum. Well, let's keep going with this and see what happens. Let me take this and turn it down all the way as low as it will go, 3,500. In fact, if you want to be exact here, you can always type into this box in the middle of the dial. So let me type in 3,500 there and click outside, and it sets the control. So let me go down here again. So once again, keep your eye on the ball down here, and I'll go up and I'll hit the model button. Okay, so you can see that the color changed again. The star is now an even deeper orange, in fact closer to red here towards the edge or the limb. So we are now simulating a star whose color is distinctly red. We are now simulating a star that would look like one of these red ones in this Hubble Space Telescope image that we were looking at earlier, maybe something like one of these stars. So that's interesting. Based on the experiments we've done so far, we can now conclude that these redder stars have lower effective temperatures than the Sun, maybe effective temperatures around 3,000 to 4,000 or 4,500 Kelvin or so. And so again, some famous bright stars in our sky that have that color are stars like Betelgeuse in Orion and Antares in Scorpio. So let's go back to gray star 3 here, and let's go the other way. Let's now try turning the temperature up from that of the Sun and see what happens. So first of all, I'm down here at 3,500 Kelvin still. I want to be careful about this and go back to my reference object, the Sun, before I do anything else. So what am I going to do? I'm going to go up here to the escape hatch and hit the reload button. And when gray star 3 reloads, all these parameters, including the effective temperature, go back to those for the Sun. Okay, so let's grab this dial, and this time let's turn it up. Now as you go to hotter stars, small temperature changes aren't as significant. So let's go ahead and just crank this up a couple of thousand Kelvin from 5,800 to about 7,800 or so. So that's close enough. So I've just turned the effective temperature up by 2,000 Kelvin from that of the Sun to about 7,800 Kelvin. So I'll come down here and keep your eyes on the prize here, and I'll hit the model button. And you can see what's happened to the star's color. There's still a little bit of yellow in it, but it's now looking much whiter throughout the central region here, so something's happening as we go up in temperature. Let me grab this and turn it all the way up to 10,000 Kelvin. So I'm increasing the temperature by something like 4,200 Kelvin above that of the Sun. So there we go. There's a temperature of about 10,000 Kelvin. And let's go down here and hit the model button. Keep your eye on what's going to happen to the image of our star here. And look at that. That's interesting. With an effective temperature of 10,000 Kelvin, the star comes out white in color. So if you know a little bit of color theory, then you may know that in order to make white, you need to have equal amounts of all the basic primary component colors, such as red, blue, and green. Mixing equal amounts of component colors is how you get white. So that's interesting. That tells us that if a star has an effective temperature, a surface temperature of about 10,000 Kelvin, then that star is shining equally brightly in all the different primary colors, and so it comes out looking white. And a famous star in our night sky that has a color of white is Vega in the constellation Lyra, so we can conclude that Vega has a surface temperature of about 10,000 Kelvin. Okay, let me go back up here again and just do one more experiment. I'm going to grab a hold of this, and I'm going to turn it up by another 10,000 Kelvin. I'm going to double the temperature and go all the way up to 20,000 Kelvin here. So again, once you go to hotter stars, smaller differences in temperature are less significant. So there we are with an effective temperature of about 20,000 Kelvin. So let me come down here and we'll look at the image of the model, and I'll hit the model button. And you can see what happens. The color of the star turns distinctly blue. So at 20,000 Kelvin, we are now modeling a star that looks something like this one of these blue-white stars. Okay, and a famous star from our night sky that's bright, that has this blue-white color, is Regulus in the constellation Leo. And so we know from this that Regulus has a surface temperature of about 20,000 Kelvin, actually a little bit less, about 18,000 Kelvin. So now we know the basic reason for these different colors is that these stars have different effective temperatures or different surface temperatures. But we don't want to just stop the story here, though. We should think a little bit about why a star's color should depend on its effective temperature or its surface temperature. And that really begs a more basic question. Why do stars glow at all with light of any color? And the reason is because stars are dense, opaque objects that are hotter than their surroundings. They contain excess heat relative to their surroundings. And so in that situation, the object tries to cool itself off by emitting excess heat energy through its surface in the form of radiation. So we saw earlier in this video that light is a form of radiation, radiant energy, and so the light or the radiation that is leaving a hot object like a star represents excess heat that that object is shedding as it tries to cool itself off. So this kind of light or radiation that a hot, dense object emits as it tries to cool off is known as thermal radiation. So thermal is a word that means heat, and so this is radiation that's emitted by dense objects that have excess heat. There's another nice old word in the English language to describe this radiation. It's also known as incandescence. So thermal radiation, incandescence, those are synonymous terms. They both refer to the same thing. And that term, incandescence, might ring a bell with you because ordinary household light bulbs, as you may know, are known as incandescent light bulbs. And the reason is because they glow for the same reason that a star does. When the tungsten filament in a light bulb gets very hot, if you run electric current through it, it gets very hot. It's a dense, opaque object like a star is, and so it tries to cool itself off by emitting light, radiation through its surface, and that's what makes the light bulb work. So once again, I'm going to go to a Wikipedia page here. Here's a Wikipedia page on incandescence or thermal radiation. And let's have a look at this image here. What's remarkable is that for any object that's dense and opaque, it doesn't matter what it's made out of or what state of matter it's in. If you take any object, such as this piece of iron here, and you heat it up so that its surface temperature is much greater than about 3000 Kelvin or so, then the incandescence or thermal radiation that it emits will be visible to the human eye. So it will look as though the object is glowing with its own light, just like stars do. And what's more, the color of the incandescent glow from that object will depend and only depend on the object's surface temperature. So here we have a bit of iron that's being heated up in a blacksmith's furnace to what looks like about 3,000 or 4,000 Kelvin or so, and at that temperature the object glows with sort of a red-orange light, just like stars do, whose effective temperature is in that range, 3,000 to 4,000 Kelvin, stars like Betelgeuse and Antares. If we were to take this object and heat it up even more, say to surface temperatures of about 6,000 Kelvin, then that object would glow bright yellow like the sun. And if we were to take this thing and we could somehow heat it up to temperatures of 20,000 Kelvin or so, like the star Regulus, then it would glow with a light that's blue-white in color. That's just a property of incandescent radiation. But the remarkable thing is that the color of the incandescent glow being emitted only depends on the surface temperature. It doesn't depend on the composition. It could be a piece of iron, or it could be a gas with whatever composition a star has, and it doesn't depend on the state of the matter. It could be a solid object like this one, it could be a liquid object, or it could be a gaseous object like a star. That doesn't matter. The color only depends on the surface temperature. But the best part of all of this is that now that we understand why different stars have different colors, we can actually turn the reasoning around and go the other way. That we can use the color of a star to determine its effective temperature or its surface temperature. And remember from our discussion of photometry that we can measure and express the color of a star very precisely using numerical quantities, and that actually gives us a powerful thermometer. It gives us a thermometer for diagnosing the surface temperature of stars, even though they're very remote, just by measuring their color and understanding that the light is incandescent. So this is actually how astronomers routinely measure the surface temperatures for lots of stars. So this is real astronomy. So just to review what we've done this time, we started off by asking about the colors of stars, and that led us to discover the first fundamental stellar parameter or property, namely effective temperature or surface temperature. But along the way, we also picked up a number of other important ideas. Use of the Kelvin temperature scale or the absolute temperature scale. The idea that light is a form of energy and that we can measure the brightness energy of a star or the flux, and that we can measure the flux through color filters to measure a star's color precisely, a procedure known as photometry. So these are ideas that are going to recur throughout this video series, so it'll be good to keep these ideas in mind. One thing that I'm going to do towards the end of each of these videos is suggest a pedagogical activity for teachers and instructors based on what we've talked about. So in this particular case, an activity that I can suggest that's kind of fun if you are working with students who are at a level where they are comfortable with the concept of temperature, that they would be comfortable thinking about the Kelvin temperature scale as compared to the Celsius temperature scale, then an activity that you could do in the classroom or that you could have students do individually or in small groups is the following. You could show students an image like this one, either using a classroom data projector or having students look at the image themselves on their own classroom PCs or tablets or whatever they're using. The important thing is that you give them an image that shows very clearly that stars come in distinct colors. And so a star field image from the Hubble Heritage Gallery would be a good choice. In fact, the Sagittarius star cloud would be a good choice. And then what you could do, the activity is that you could have students load the Greystar 3 virtual star simulator in a web browser using classroom PCs or using their own tablets or whatever they have, and just play around with the input controls to see if they can match the colors that they see in the image. Okay, so you may wish to draw the effective temperature knob to their attention as being the property that they should adjust. Of course, they can try setting different values of the temperature experimentally, hit the model button and see what happens to the color of their simulation here, just as we've done today. And you can challenge students to see if they can match with Greystar 3 simulations the actual colors of some stars that they see in an image like this one. And you can tell students when they do that that they are working with real space telescope data to determine the effective temperatures of stars in just the same way that real working astronomers do. So as always, I will end the video by reminding everybody that if we go back to the Greystar 3 simulator page here, if you go up one level on the URL, then you get taken to the main Greystar 3 page. And there are a number of resources here. This is the page from which you can run the Greystar 3 simulator. Let me just go back again. But there are other things here. There's a blog for people to share information about lesson plans and projects and things like that that incorporate Greystar 3. There is a link here for people who want to install their own local installation if you want to use this or have your students use it without relying on a connection to a remote web server. So I encourage you to check out the main Greystar 3 page and see what resources are there. Okay, so in the next video, in episode 2, we will move on and introduce two more basic properties of stars for which it makes sense to talk about them together, namely mass and radius. So thanks for joining us for this video, and we'll see you next time.